bevor wir mit unserer Wiederholung auf Englisch weitermachen, vorher kurz zwei organisatorische Dinge. Erstens, wir bieten Ihnen heute nach dieser Veranstaltung und nach einer Tutorübung, die heute Nachmittag auch stattfindet, ab 16:45 Uhr im Seminarsaal meines Lehrstuhls, das ist der Raum N1135.
Gehe ich da hin zu solchen Stunden? Das ist wahrscheinlich die Sprechstunde, oder?
16:45 Uhr eine Fragestunde ab. Also wer Interesse hat und über offen gebliebene Probleme fragen und darüber diskutieren möchte, ist da gern gesehen.
Haben Sie das gesehen?
Der zweite Punkt ist, wir bieten Ihnen ja, das ist ja inzwischen freigeschalten worden, die Anmeldung dafür, dieses Praktikum, das in den Räumen und mit Unterstützung der Firma Rode und Schwarz stattfindet, an. Und es waren noch Fragen an Herrn Lehmeier bezüglich der Anmeldung. Die 80 Plätze, die wir zunächst eingeplant hatten, sind praktisch total belegt inzwischen. Und die Frage ist, wer noch nicht angemeldet ist und trotzdem großes Interesse hätte, bitte jetzt melden. Dann können wir sehen, ob wir noch etwas organisieren können, sodass wir sie auch noch unterbringen. Das ist eine eher überschaubare Zahl von, grob gesagt, vielleicht mal 15, 20 Leuten. Okay, gut. Wie machen wir das dann? Machen Sie dann die Anmeldung nochmal auf, dass es sozusagen eine Warteliste gibt.
Brownie, aber dann schuldest du mir eine
Also Herr Lehmer erklärt das. Gut.
Brownie ging umarmen.
Well, now back to
aber dann später.
our
Das kann ich
scientific
irgendwann mal
topic. Although I tried to talk with you already on Tuesday about this topic, but then the student assembly prevented our meeting. So now we repeat a lot of things which we have done last week. The main thing which we have been dealing last week was the solution of the state space equation, which is a coupled set of ordinary differential equations. So, and we have looked only on the homogeneous case. So, at this equation, x dot, the vector x dot is equal to the matrix A times x of t. And we have to choose an initial value anyway, which I call x0. And if you think back to the first order case, where the state space variable is only a scalar, there we have the situation that the solution was simply found by this equation, that the solution is this exponential a times t minus t0 times the initial value, and let us arbitrarily put t0 to 0 seconds, then it's this. And if we apply the same strategy for the vector case, then we run into the situation that we have to deal with a matrix exponential. An exponential function where in the exponent there is not only a scalar but a matrix. And well, what is this matrix? Well, it's simply defined with its Taylor expansion, like in the scalar case. What you most probably know from high school is that the exponential function e to the power of x is given by this power series here, and we simply replace the x by the matrix A, that's it. And this is the way how we get the matrix exponential. The problem is, this is not numerically efficient to compute the solution. It's possible, but it's not efficient. So we look for alternatives to that.
So we can
and one alternative first is, again, start with our matrix valued ordinary differential equation, again, stick to the homogeneous case, and make a solution like in the scalar case with a vector initial value, but in the exponent put simply a scalar instead of the matrix, and try it out how this works. We plug it in, we compute the derivative with respect to time of this solution, and then we plug it in on the left and on the right-hand side of this first equation, multiply both sides with e to the minus lambda t, and end up with this equation. So we have then bringing everything to the left-hand side, or to the right-hand side, we have an A, we have minus a identity matrix times lambda, and both of them multiplied with the vector of the initial values, and what remains on the other side of the equality sign is the zero vector. And with that we could compute the zero vector by simply multiplying from the left-hand side with the inverse. But then we get only what is a trivial solution, which is not useful. This is mathematically valid, but it's practically not useful, because it tells us that this solution is valid only if the initial value is zero. And if the initial value is zero, then the solution is zero for all time. So what have we achieved with that? Nothing. Therefore, we have to take care that this inverse doesn't exist. So we have to make clear that the determinant of A minus lambda identity is zero, because that is one way to express the fact that the inverse of A does not exist. And that leads us to a quadratic equation simply. So we compute that determinant of our state matrix A minus lambda times the identity matrix, and that leads to this quadratic equation where capital T is the trace of the matrix, of the state matrix, the trace of A, which is simply the sum of the diagonal elements. With every matrix, the trace is always the sum of the diagonal elements. The delta is the determinant of the matrix A. And obviously, quadratic equations have normally two solutions, and the two solutions are given here. Half of the trace plus minus square root of half of the trace squared minus the determinant. We can compute that, and we know, of course, that there are different possibilities. We can have two real valued solutions. They can be negative or positive. One could be negative, one could be positive. They could be real and equal. That's then the case when t squared over 4 is equal to the determinant, so that the expression under the square root is 0. Then both solutions are t over 2. And it could be complex conjugate if the term under the square root is negative. That later. First, as soon as we have these two lambda values, that means there are only two very specific lambdas which we can use there in constructing the solution. This is not arbitrary, the lambda which we can choose. And with the lambda, we can choose the so-called, the lambdas are the so-called eigenvalues, and now I take again this equation, A minus lambda identity times x0, and replace the x0 with another letter, q index 1 or q index 2, dependent whether I take lambda 1 or lambda 2 in that equation. And that determines us the so-called eigenvectors, the eigenvector q1, which belongs to the eigenvalue lambda 1, and the eigenvector q2, which belongs to the eigenvalue lambda 2. Since we have taken care that this matrix does not have an inverse, by choosing the proper lambdas, it's clear that the matrix is rank efficient. It has linearly dependent rows and columns. So this is not a linear set of equations where we can really uniquely determine the solution, because the set of linear equations is rank efficient. Anyway, there are these two equations, and again, I would like to draw your attention to these equations because they are really important, and it's important to have a geometric picture in your brain for that. It simply means take that vector q1 multiplied with a matrix that normally is a rotation in space and either stretching or what is stauchen in English? I don't know. Shrink, yeah, thank you. Either stretching or shrinking. But this equation requires, well, it's simply the same vector multiplied by a scalar. So it looks in the same direction in space, it's only a stretching or a shrinking, but no rotation. And that is something very specific. And for the 2 by 2 matrix A, there exist at most only 2 vectors which have that property. And the eigenvalue, that's the factor which stretches or shrinks, depending on if it's larger than 1 or less than 1. By the way, there are special situations where a matrix can have many eigenvectors. Look at the identity matrix. What are the eigenvectors of the identity matrix? Any vector. Because any vector multiplied with the identity matrix gives the same vector. And what are the eigenvalues of the identity matrix? Well, it's a diagonal matrix. And in a diagonal matrix, you see the eigenvalues as the diagonal elements. So the eigenvalues are ones. Simply. Okay. So we can determine these eigenvectors with these equations, but only as far as the direction is concerned. The length, the norm of the eigenvector is an open issue. In many situations, people choose to make eigenvectors of norm 1. But that is arbitrary. It could be any other norm. And the way we have determined the eigenvectors gives some norm which we have not controlled. Okay? Taking the 2 eigenvectors and put them aside as 2 column vectors of a square matrix, which we call the modal matrix, capital Q, we can write these 2 equations, pull them together, and write A times Q1 and A times Q2, these 2 vectors, here. And we know they should be equal to lambda 1 Q1, lambda 2 Q1. And that could be, again, written as the modal matrix times this diagonal matrix with lambda 1 and lambda 2 at the diagonal places. So we have A times Q is Q times lambda, where lambda is diagonal. And the diagonal elements of lambda are the eigenvalues. Okay, now this equation we can multiply from the left with Q inverse, then we are getting this one. Q inverse times A times Q is equal to lambda. We can multiply it with Q inverse from the right, then we get A is equal to Q times lambda times Q inverse. The second thing is called the eigenvalue decomposition of a matrix. You have a matrix and you decompose it into 3 matrices, a product of 3 matrices, Q, lambda, and Q inverse. And the properties are, the third one is the inverse of the first one, and the one in between is diagonal. This is not always possible. This is only possible if the matrix A is similar to a diagonal matrix. Because the transform, which we make here, where A is multiplied from right with Q and from left with Q inverse, this is a so-called similarity transform. And the similarity transform preserves the eigenvalues. Preserves a lot of other things also. Preserves the trace, preserves the determinant. Okay, and that is a really nice thing we can use in the following, to propose another way to find the solution. But first, we look again at the computation of the eigenvectors. Here for the eigenvector Q1, the same applies of course for Q2. I have multiplied simply this system in detail out. A11 times Q11, A12 times Q12 is equal to lambda 1 Q11, and the second row with that vector gives the second equation. And they are, as already mentioned, linearly dependent. And here I have made a simple choice. I said, let us make Q11 minus A12. You could take any other number. That is not important what it is. This is leading to a very simple expression for the second element. Because if we plug that Q11 in here, and then use this equation to compute Q12, we get for Q12, A11 minus lambda 1. And with Q2, the same with lambda 2. So these are 2 solutions for these 2 eigenvectors. They have some norm, I don't know what it is. I could of course compute it, but it's not controlled. If you would like to have norm 1, then you simply have to square this element, add the 2 and take the square root, and divide the whole vector by that. Then it will have norm 1. So now from the outset we see now we have two lambdas, two q's, so we have two solutions. Initial value for the solution with lambda 1 is q1, initial value for the solution with lambda 2 is q2, and the complete general solution is any linear combination of the two. And how these coefficients C1 and C2 have to be determined depends on the true initial value which you choose for the solution. So if you say I have some initial value x at time t0, well, I have to find two coefficients C1 and C2 such that the linear combination C1 times Q1 plus C2 times Q2 is equal to the initial value I would like to use. And that should always be possible as long as Q1 and Q2 are two linearly independent vectors. They span the whole plane, so any point in that plane can be written in these coordinates. Okay. But now, since we have this nice model matrix Q, we can apply a coordinate transform. And the coordinate transform simply is take our state vector x and multiply it with Q inverse. That gives you a new vector where I have simply chosen the symbol psi. If we take the derivative of psi, it is obviously the same matrix Q inverse times the derivative of x. That's because the matrix Q inverse is a constant, and that's the constant which in taking derivative simply stays in front there. Now, if we take now our equation, x dot is equal to a times x, and plug in for x dot q times psi dot. For a, we plug in the eigenvalue.